So the title of my talk today is Classical Gravitational Wave Tales from Soft Theorem. So let me begin by giving a brief introduction to the problem that we'll be trying to address. So let's suppose that we have some violent explosion in space where some stationary system breaks apart into fragments. So this process will emit gravitational wave, and this gravitational wave will reach the detector, some detector D that's placed far away at some later time. We can also consider a more general situation, which is the case of collision, where you have a set of objects which come together, interact, and then fly apart, possibly fragmenting and coalescing during this process. And this will also produce gravitational waves. Now, in general, if you want to compute gravitational waves produced during such process, it's a complicated problem. And it's complicated because of two reasons. First of all, when the objects are close, then they may undergo complicated non-gravitational interactions. And this is what happens, for example, in the case of explosion of a supernova. The second reason that it's complicated is that gravity is described by nonlinear partial differential equations. So even if the interactions are purely gravitational, as in the case of, say, black hole merger, the analysis is complicated. We really need numerical methods to compute gravitational waves that's emitted during this process. However, it turns out that some results in quantum theory of gravity, namely soft graviton theorems, can be used to get analytical results on some aspects of classical gravitational wave, and this will be the focus of this talk. So what I'll describe in this talk is based on some work done during last few years with various collaborators. Of them, Biswajit Sahu, who is in the audience, he has been the architect of many of the results that I'll be describing. And a short review of these results can be found in this. So most of what I'm going to describe in this talk can be found in this short review over here. So let me begin by setting up the convention. So I'll not set any of the fundamental constants to 1, at least initially, so that we can, if we want to get some numbers, we can easily get it without having to put in explicitly extra factors of C and Newton's constant and h bar. So I'll be using the mostly plus signature metric. So eta will be diagonal matrix of this kind. All the indices will be raised and lowered by eta, not by the metric. We'll define the fluctuation in the gravitational field in this way. So h mu nu will be a dimensionless quantity. And it will often turn out that it will be easier to work with a slightly different quantity than h mu nu, which is called the trace reversed metric. So E mu nu will define by subtracting some trace part from h mu nu. But we don't lose any information by looking at E mu nu because we can reconstruct h mu nu once we are given the value of E mu nu.
So there are no h bars in this talk?
There will be no h bars, yeah.
And do they show up?
They will show up in the intermediate stage when we discuss soft theorem, right? But at the end the h bars will cancel. Okay. Yeah, so the results will have no h bar. Okay, so I'll begin by giving the summary of the results. So we'll consider this general situation, where you have a scattering in space. We'll imagine that you have a set of objects of 4 momenta which will denote by p1 prime to pm prime, which come together, interact, and then they disperse as a set of objects with 4 momenta p1 to pn. So here is, I have described a picture of the scattering. So this region, this is a region in space-time which we'll call the scattering region, where most of the interactions take place. And we'll just choose the origin of space-time to be inside the scattering region. Okay, the precise definition of where the origin is will not be important. But we'll, just for convenience, we'll just choose the origin to be somewhere inside the region where the scattering takes place. And once the scattering happens, the gravitational waves are emitted from during this process, and the peak of the signal will reach some detector D that's placed far away at some time t naught. And our goal will be to examine the order 1 over r contribution to the waveform. So if the detector is at a point r, if the detector is placed at a distance r away from the region where the scattering takes place, okay, we'll look at the order 1 over r contribution to the waveform, but that's the radiative part. Okay. Here r is just mod of x. So we'll define retarded time, okay, which is defined here, t minus t naught. Okay. Now, as I said, t naught is the time when the peak reaches the detector, but peak may not be a well-defined notion. Okay. So the definition of u, we should take only up to shifts of order 1 or up to constant shifts, and all the results that I will be specifying will be independent of that constant shift in the definition of u. And our focus will be on the late and early time tail of the wave, okay, which means that the value of h mu nu at the detector at large positive u and large negative u. Okay. The reason is that the soft theorem tells us only about this information, how h mu nu behaves at the detector at large positive u and large negative u. So the result that I'll be trying to elaborate on, okay, is that if we look at again term proportional to R inverse, we'll have nothing to say about higher order terms. Okay. Then at early time, okay, E mu nu has a u dependence of this form. So there is a leading term which is 1 over u times the coefficient C mu nu. Then there is a subleading term u to the minus 2 log of mod u, and then there are higher order terms. At late time, okay, it's similar except that E mu nu also acquires a constant piece. I should also say here that the fact that in early time E mu nu doesn't have a constant piece, that's just a choice of convention, because a constant piece of E mu nu is like adding a constant to the metric, and we can always change our coordinates to make that constant vanish. Okay, so you just assume that at early time the metric is just eta mu nu. Okay, so absence of constant here is just a convention. Perturbative calculation. Well, the result will not be perturbative. Okay. The result will be exact. Right? Yeah. But we'll see how the result comes.
But in principle, you compute the 1 over r correction. So.
1 over r square correction?
Yeah, 1 over.
1 over r square, in principle you could, but those are not radiation, right? So in practical, from practical viewpoint, I mean, if you think of some collision happening far away in our galaxy or in our universe, r is very big. Right? So 1 over r square effects we never see. Right? We are capturing only the radiative part, because the soft theorem is about radiation, right? So that's the part we'll be able to capture. Probably, but I presume this is the only thing that you need for the leading order behavior, but I'm not completely sure. Pardon?
The non-radiative parts of the metric, right? Equations, and those might not be at that.
At 1 over r.
Or at least not 1 over r radiative.
Sorry, okay, there one more question, yeah?
Are you assuming that all of these gravitational waves are produced in the scattering process, or what's the gravitational radiation look like on Scrim minus, like the incoming radiation?
Yeah, so incoming, okay, there may be, the incoming particles may contain massless particles. Okay. I'm not assuming that the incoming particles don't contain massless particles, but those will go in the data.
Okay.
So when I said that the result is given in terms of the incoming and outgoing momenta, if there is incoming radiation, that data will also go in this formula that I'll be describing. Yes.
Is this result?
Yes, yes. I mean, you are not doing a G Newton expansion. Okay, so I'll give the formula for these coefficients. Okay, then perhaps it will become a little clearer what this really means. So here are the formulae. Okay, it looks a bit complicated, right? But the important part is not the details of the formulae, but the fact that they exist. Okay? So, as promised, you can see that the result depends essentially on the momenta, right? So p primes are the incoming momenta, p's are the outgoing momenta. Okay? And two other things, this r is a distance that I have already introduced, and n is a 4 vector, okay, whose first component by choice is 1, and then the other component is just a vector x over r. So n is really a null vector, right? It's describing the direction in which we are observing the radiation. And yeah, so as I said, everything else that it depends on are just momenta and masses of the incoming and outgoing particles.
I have a question.
Yes.
You just said this result is G-Newton exact, but you also have a U expansion, right?
Yes.
So is this U expansion actually equivalent to the G expansion?
Yeah, U expansion basically get correlated to the G-Newton, indeed. Yeah, so if you look at just 1 over U piece, right, which is what these are describing, then there is no further G-Newton correction.
Okay. Sorry.
Yes.
Also a nonlinear contribution to A from the gravitational radiation itself?
Yes, there is, but that's included in this P, because the sum over P includes also the gravitational radiation that is coming out. Right, so that's I think the nonlinear part that you're talking about. Because we have to look at the fully incoming states, full outgoing states, and that's what enters this formula. Is that what you meant? Or?
Yeah, I guess we need to have knowledge of the power spectrum of the radiation emitted to be able to use this formula then.
Yeah, we'll see that there is a twist to it, right? Yeah, at this stage, indeed. So we need to know the gravitational power spectrum to be able to use this formula. But eventually we'll get around that. Yes. Yeah, it is a completely classical formula. No, I'll describe a classical derivation of this. Yeah, exactly. So this formula doesn't tell us what the final momenta are, right? This tells us that if we knew the incoming momenta and the final momenta, then what will be the gravitational radiation from this? Indeed. Yes.
Expansion.
Yes.
What is the so U is dimensionful. So what is the coefficient? So is it?
Yeah, it's not okay. Part of it is U over capital R, right? Which is because of the Coulomb drag. Okay. Part of it is U over the size of the system, the scattering region. So we can distinguish between the two, but I'll not try to distinguish it in this formula.
Unless you treat it like these perturbinos.
Yeah, so I'll describe the way we derive it classically, right? I'll describe both the soft theorem, which will be more somewhat impressionistic argument, but I'll describe also how we derive it classically. Right? I think that will make it clear what goes in deriving this formula. Okay, so here are the formulae for the F and G. Okay, the coefficient of the 1 over U square log U. Okay, and as you can see, it's more complicated, but eventually it doesn't use any more data, right? It just uses the incoming and outgoing momenta. The other thing I want to point out here is that G, which is the coefficient of the 1 over U square log U in the past, right? This you can see only depends on the P primes, which are the incoming momenta. So that radiation in the past depends only on the incoming momenta, but the radiation in the future, which is the F, okay, that depends on both past and future momenta, right? It depends both on P prime and P. Yeah, it's independent of spin. So to this order, it doesn't matter if the particles have spin. Right? The spin dependence come at order 1 over U square, and I'll just describe some aspect of this. So we didn't assume here that the particles are spinless. Okay, so now let me describe some features of this formula. So A mu nu is the well-known memory term. So what it describes is a permanent change in the state of the detector after the passage of the gravitational wave, because you can see that the metric doesn't return to eta mu nu, but it returns to eta mu nu plus this a mu nu. Okay. And these are of course known from early days, but the work of Andy and Sasha essentially related this to the soft theorems. Okay, so that's in fact the starting point of relating expansions of this kind to soft theorem. Okay. So these are what are called tail terms, okay, and these were derived in the various works that I referred to earlier. Okay. But these were also observed earlier in special cases. Okay, it's just that the universal formula for these tail terms were not known earlier. Okay, so now I come back to the question of the dependence on the outgoing gravitational radiation. So if you look at the expression for these objects, a mu nu, b mu nu and f mu nu, okay, then the sum of the final state particles include integration over outgoing flux of gravitational radiation. Okay. So let me just show this again. Okay, so let's look at the expression for f mu nu. Okay. Here you see there is sum over final state particles and sum over incoming particles. This final state will in general contain finite energy gravitational waves that are emitted during this scattering process, and if you want to evaluate f mu nu, you have to include the contribution from those. Okay, so those will appear as some kind of integral over the flux of gravitational waves, the whatever momentum the gravitational waves carry. Okay. This had been well known from the study of memory effect, okay, and for a mu nu, this is what is called the non-linear memory term. Okay, the contribution to the memory due to the finite energy gravitational waves in a final state. It turns out, however, that due to some miraculous cancellation, okay, in b mu nu and f mu nu, okay, the tail terms in the future, the contribution from massless final states can be expressed in terms of the massive state momenta. Yes.
I try to look at the original like constraint equation, I would have thought that all the tower of tail terms could affect like the nu squared, like nonlinear memory effect. And like, is that what do you actually see that there's like, do they cancel somehow is what you're saying, or what are you exactly?
Yeah.
So plug it back into the constraint equation.
Yeah. So let's just go back to this formula.
Yeah.
Look at the formula for f mu nu, right? So here, a priori you are supposed to sum over all final states, which includes the gravitational waves that are emitted during the process.
Sure.
Right? Now, those are massless particles, so you can set m equal to 0 for those particles,
And
right?
then,
What I'm saying is that if you set m equal to 0 and just manipulate this formula,
yeah.
okay, you find that you can drop the sum over final state massless particles
Yeah.
and add some compensating term, which I'm going to describe what compensating term you.
Yeah, I guess then my question is like, if I plugged into Andy's constraint, like the constraint equation for UU, I would have like memory equal to the nonlinear part plus the matter sources, and I would have thought the first term you wrote down, this A, would look like
so for
the
A
one
there is
and
no
not-
simplification.
Yeah.
So for A you cannot do anything, right? It's only for the other two, the tail terms, that this simplification occurs.
Okay.
That the contribution for massless states, right, can be dropped, provided you add some compensating terms, but those depend only on the massive state momentum.
Okay.
So let me give the formula, and then I think it will become maybe somewhat clearer. Okay, here is the formula. So what it turns out that in b mu nu, okay, we just drop all the massless particles and radiation contribution from the final state, okay, and then we compensate for it by just adding this term, okay, where pi is the total incoming momentum, and pf is the total outgoing momentum, but carried only by the massive particles. Similarly, in f mu nu, we drop all the massless particle and radiation contribution in the sum of our final state and compensate by adding this term. So what I want to emphasize is that these are not new formula, right? You don't have to do any, you don't have to know any physics to derive this formula. You just take the formula that I gave you, formula for f mu nu, set some of the particles to be massless, right? And you can show that you can just manipulate the contribution from the massless particles so that they are replaced by this combination over here. So this must have some deeper understanding, okay, which we don't have, right? We derived this just by manipulating the formula. We looked at the final formula and we just manipulated it, okay, setting some particles to be massless, and we found that the massless particle contribution can be rewritten in terms of the massive particles. So this means that the tail term computation doesn't require you to know what kind of gravitational waves got emitted during this process, as long as you know what the total massive particle momentum is in the final state. I don't know, is that, does that clarify or it?
No, I mean, it's interesting. I guess I don't appreciate what's actually going on if it's like, I think I had a separate question than like I would have a question now. The first question I would have had is that like I might have thought it's very complicated to see then the ward identity because you now have a bunch of tail terms that could contribute to nu squared and then sourcing the memory effect, right?
Yes.
You're saying there's a dramatic collapse where it's very simple now or not?
Yeah, for the tail terms, what I'm saying is that those effects simplify and they can be rewritten in terms of this formula. You just drop all massless particle in the final state and you write in this formula.
Are these calculations done in a particular gauge or are they gauge invariant?
No, we did it in redundant gauge, but you can check gauge invariance of this formula. Right? For example, if you contract the formula that I gave with n mu, right, which is the direction of the momentum, it vanishes. Yes.
Does this mean that there's a non-trivial relationship between the massive outgoing momenta and the radiation that, I mean, do you have a formula of that kind that is relating the two, or?
Well, the only relation we use is total momentum conservation, right? Total momentum carried by the massless final states plus massive final state should be equal to total incoming momentum. Right? That's the only thing that we used. Right? But it's not obvious that that itself will allow you to just rewrite all the massless state contribution in terms of massive state contribution.
So you're saying that's the only input, and then
that's the only input. Yeah, that's the only input. So anybody can just take this formula and set some of the particles to massless. It doesn't matter how you derived it, right? Just manipulating this formula, we can arrive at this conclusion. As I said, this must have some deeper understanding of why it happens, right? But we don't have. We just got it by manipulating the formula.
And could it be something related to like you're taking these constraint equations and then you're doing these integrals and like there's a divergent log that maybe is universal or something or not?
Yeah. So okay, I'll describe the derivation, okay, of this formula. I have not done that so far. Right? Then maybe it will, I mean, some of you may be able to see why this is the case, but at least we couldn't see any deeper reason. Okay. So this formula that I wrote down is for neutral particles. Okay. So if the incoming or outgoing objects carry charge, then there are additional terms in the formula, right, because of the electromagnetic interactions. Okay. So those are known, but I have not written them down. Now I started by describing explosion, but explosion of course is just a special case of scattering, where the initial state has just one object. In this case, C mu nu and G mu nu will vanish and E mu nu takes this form. For binary black hole merger, the final state has just one massive and many massless objects. So in that case, we can simplify the tail expressions by using the formula that I described here, okay, this replacement formula over here, these formulae over here. And what you find is that the coefficients of the 1 over u and log u over u square terms vanish. So for black hole merger problem, right, there is no tail of this kind.
Interesting.
Now, one can ask how big are these effects? Okay, so we did some estimate. So if we have a core collapse supernova in our galaxy, okay, then what we found is that this could produce a strain. I use this. That a core collapse supernova could produce a strain of order 10 to the minus 22, which is basically at the edge of LIGO sensitivity, okay, after 1 second. Okay. But for this, we have to choose the parameters favorably. Okay, used the maximal possible velocities that we know of neutron stars that they possess. Using that, we got this number 10 to the minus 22. We also calculated for the bullet cluster, right, which is like two superclusters of galaxies passing through each other, right? So that's also a collision process. For this, the strain in fact is much larger, 10 to the minus 14. Unfortunately, it's not observable because the strain changes over a scale of about 100 million years, right? Because that's the time scale over which the bullet clusters, clusters are moving. Pardon?
Did you use the matter? Sorry, did you use the matter outflows in part 1 or the neutrinos?
For the neutron, yeah. So we assume that the neutron star gets a kick, and that kick is because of the matter outflow, not neutrino.
Okay, all right.
Yeah, because if there's a neutrino, then there'll be no effect, right? So you can say this 1 over u is a test of whether the kick of the neutron star is because of the matter outflow or the neutrino outflow.
So it has to be affect massive particles.
It has to be massive
Okay,
particles,
okay,
exactly.
thank
So
you.
outflow has to be massive particles, indeed.
So you said it's 10 to the minus 14 over 100 million years, but if I observe for tens of years, will it be 10 to the minus 20 something? Could you imagine?
Yeah, we could, but I mean, it will take a lot of years, right, to really see this. Yeah.
Imagine over 10 or 100 years having like a tiny fraction of this strain and be able to observe that.
Maybe, yeah. I mean, yeah, you can just scale it, right? I mean, you just multiply it by appropriate ratio. Okay, so now I'm going to give the outline the derivation from soft theorem, and then I'll also outline the derivation, the direct classical derivation. Okay, and for this we'll now set c equal to 1. Yes.
So you said for the binary black hole module there are no tails.
Yes.
Is that just like 2 to 1 scattering thing, or is it like some property of black holes are needed?
No, that's 2 to 1 plus massless particles. Yeah. So anything which has not even 2. In this is you think of this 1 to 1 plus massless particles because the initial system is bound, right? So you think of the one object. So 1 going to 1 plus massless, right? That doesn't produce any tail. Neutron star, if you have matter emission, right, then in principle there is a 1 over neutron, right? So the radiation emission doesn't produce 1 over neutron, but matter emission will. Yes. Well, if it's a bound state merger, then the initial what I described as 1 over u tail initially, right, that will be masked by all the radiation that is coming out. Okay, but the final state, the final state tails will still be there. So we are assuming here that the incoming and outgoing objects that are there, those are gravitationally inactive. That those by themselves don't have some sending out pulses, for example, right? Then of course it will be swept by those signals.
Statement that there is no tail because binary is not spherically symmetric. So I think.
Yeah, binary is not spherically symmetric. Yes.
So it's going to recoil when it emits the gravitational radiation. So it's going to be a PF.
Yeah, only one massive particle will recoil. That if you use that the formula that I gave you, one massive particles from many massless particles, the result is 0. We need at least 2 massive particles in the final state.
Why is that?
Okay, sorry, I'm worried a bit about the time. So think about we have to close shortly. So
Okay.
I mean, if you want to take the questions, you're free. But
Yeah.
you know,
So basically, you substitute in this formula that I gave. You drop all the massless particles and replace, add that extra term, and you find that with one final state, if the initial state has only one object and the final state has one massive and many massless particles, the result just vanishes. Okay, so let me just give the outline of the derivation using soft graviton theorem. So in quantum field theory, the scattering amplitude gives the probability amplitude for transition from one state to another. That is, this of course you know. And mod a square is the transition probability. So let's suppose that we know the scattering amplitude A for transition from some incoming state P to some outgoing state Q. where both P and Q can contain set of particles. Now, what soft graviton theorem gives us is that it gives the transition amplitude for P going to Q plus some low energy gravitons. That's basically the content of the soft graviton theorem. Now we have to take the classical limit of this formula. So the way we take the classical limit is that we take the states P and Q to consist of very massive objects, and then we compute the transition probability for P going to Q plus m low energy gravitons, each say of energy h bar omega and momentum h bar omega times some unit vector, the direction of the momentum. And you have to also put a phase space volume in this formula. And then using soft theorem, one finds that this scattering probability, this transition probability has this form, some complicated quantity r which you will not need, and then a soft factor s to the m, and because you are considering m identical gravitons, there is a Bose statistics factor 1 over m factorial. So r depends on the details of the scattering process, but the soft factor s depends only on the properties of the incoming and outgoing objects. And furthermore, one finds that when you take the classical limit, which means that the energies of the states to consist of massive object or very energetic objects, then S is large in the classical limit. Then you observe that this combination has a sharp maximum at m equal to S for large S. This means that although quantum theory allows emission of arbitrary any number of particles, m can be anything in quantum theory, but in the limit when S becomes large, the distribution of m is sharply peaked around some particular value. So you can say S is the expected classical number of low energy gravitons. And the total energy carried by these gravitons is simply S times h bar omega. S is a function of the momenta.
But m is a number.
M is a number, yes.
What do you mean m equals s?
Well, m is the closest integer to s, right?
Okay, just enough.
Yeah, I mean, m is the closest integer to s. I mean, you don't distinguish between m and m plus 1 at this level because it's a large number. Exactly. Yeah, we are just looking at the peak. So this is what we learned, that the classical flux of energy carried by the gravitational wave is given by this formula over here. And now this energy flux can be translated into time Fourier transform of the gravitational wave form h mu nu. And the inverse Fourier transform of this formula for h mu nu that we calculate this way essentially gives us the late and early time profile that leads to the quoted results. Okay, so this is the way we arrive at the results that I described using soft graviton theorem. But there are some subtleties, okay, which in fact appear essentially only in d equal to 4. Okay. The first subtlety comes from the fact that the usual soft factor is infrared divergent, and we need to regulate the infrared divergence by physical principles. The second complication comes from the fact that the way I describe the analysis, it proceeds by computation of the energy flux in different frequencies. Now the energy flux is insensitive to the frequency dependent phase of the waveform because it really depends on the mode square of the waveform. Okay. So the phase of the waveform is undetermined by this analysis. So that has to be determined by separate computation. Nevertheless, we can overcome these difficulties and eventually get the results that I described. Right? So that is the outline of how we derive these results from soft graviton theorem. Now, as I said, these are classical results, so there should be a classical derivation, and that's what I'm going to describe. So direct classical analysis is certainly more complicated, okay, but it does not suffer from the shortcomings that I described, right, these problems. So I'll now describe how you go about doing this in by direct classical analysis. Here, no, here I have to use up to sub-subleading, soft graviton theorem. Leading one gives the memory, the subleading is the 1 over u, and sub-subleading gives you the 1 over u squared log u.
You validated, or you're trusting the sub-subleading is universal?
I'm trusting
that the sub-subleading soft theorem is universal, or you're deriving that it is, like it's consistent?
Well, we know that sub-subletting, there is a sub-subletting sub-graviton theorem, right? It's not universal. There are corrections, of course, but those corrections don't affect the 1 over u square log u, right? Because those come from local extra terms, and those you can check that don't affect the 1 over u square log u. So the major part of the contribution basically comes from the orbital angular momentum part of the soft theorems, and those are universal. Okay, so now let me give the direct classical derivation. So what is the goal? The goal is to find h mu nu or equivalently e mu nu that is generated during the collision process. So we are going to do this by solving Einstein's equation. So we write the Einstein's equation in the redundant gauge, and this is the form of the Einstein's equation we are going to use. Now this looks like not Einstein's equation, right? There is no non-linearity anywhere. But the reason that Einstein's equation can be written in this way is because the T mu nu, what I am calling T mu nu on the right hand side, basically includes everything that I have not written on the left hand side. Okay, so T mu nu contains the matter energy momentum tensor, but it contains all the nonlinear terms in the Einstein's equation. Okay, so that's my definition of T mu nu. Linearized terms are this. The total T mu nu. I mean, I'm just writing Einstein's equation. T mu nu. This T mu nu will have the masses of the particles, right?
I mean, I guess what I'm worried about is are you suggesting not for like the traceless symmetric thing, like the bonding mass, like.
This is a local equation, right? I'm using local Einstein's equation.
So, but the left hand side doesn't have to be just a spin to like 2 degrees of freedom. You can also have like maybe components or things like that.
Yeah, left hand side can have anything. Yeah, exactly. So left hand side, I'm not restricting mu nu to be just the transverse ones. Okay, so as I said, it looks deceptively simple, but of course right hand side depends non-linearly on E, right? The trajectories also depend on the metric. So it's a set of complicated nonlinear differential equations and may not even be known because the interactions are unknown, right? We know the gravitational part of the interaction, but we don't know what other interactions are taking place. Right? There may be nuclear forces operating on the left-hand side. Let's define E tilde, which is the time Fourier transform of E. Okay? That's what I have done here. Now we can translate the behavior of E mu nu that we are looking for into behavior of E tilde mu nu. In particular, what one finds is that if we want to look for a behavior where E mu nu goes to a constant for large positive or negative u, this corresponds to E tilde mu nu having a behavior like this for small omega. If we want E mu nu going as 1 over u for large plus minus u, then this corresponds to E tilde mu nu going as log of omega plus minus I epsilon. And if you want E mu nu to behave as log u over u square, this corresponds to E tilde mu nu having omega log omega square form for small omega. Now one feature of all these terms is that they are non-analytic at omega equal to 0. Now non-analytic does not mean that they are divergent. Non-analytic means that if we take sufficient number of derivatives with respect to omega and then set omega equal to 0, then the result diverges. Okay, so that's what I mean by non-analytic. Okay, and that will be important. Okay, so let's turn to this equation. Okay. So now this equation we can formally solve by using retarded Green's function. And this is retarded Green's function in flat space time because the box here was just flat space Laplacian. And using the explicit form of the retarded Green's function in 4 space-time dimensions, one can show that for large mod x, basically you do the time integral using a steepest descent method, okay, you find that E tilde mu nu can be written in this form, where k is determined in terms of omega and the direction along which we are looking. Okay, so this is just a rewriting of this formula. And this is the formula we are not going to analyze.
U that you're using is a U in this underlying de Donder flat metric. I mean, what's the relation to that and the actual, U of a Bondi frame?
See, near the detector, right, the metric is almost flat. That's where you are defining U. Right, because we are going to determine this E at large mod X. Because okay, we'll see how we are going to use this U. Right?
Okay.
And because we are going to use this result for large mod X, right? And where the detector is, right? That's why we'll give the detector's U. Retarded time. Okay, so we write this integral, and now the point is we can divide the integration region over y into two parts. Okay, one I'll call the scattering region, okay, which is the region of finite space-time volume, okay, where the main part of the scattering takes place. Okay. And the other part we'll call the asymptotic region, which is the complement of S. Now the point to note is that if we look at this formula, right, then recall that we are trying to look for non-analytic parts behavior as omega goes to 0, which means that we are looking for terms where by taking sufficiently large number of derivatives with respect to omega, you get a divergent result. Now if you take the derivative of this with respect to omega, right, you are going to bring down factors of y, right, as you can see from here. But if this region has finite volume, and if the energy momentum tensor is non-singular, okay, we are assuming that the energy momentum tensor doesn't blow up anywhere, okay, even though it can become large, then you cannot get an infinite result from integration over a finite volume. So this means that the behavior that you are looking for, okay, is going to come from integration outside this region, the scattering region. And in that region, E is weak because things have moved far away, okay, and we can try to use the appropriate approximation. Okay, so this I'm going to say in the next slide. Okay. So we restrict the y integral to region outside S. So in this region only long range forces are important, right? And that's the reason why if the particles are charged, then you also have to include the effect of electromagnetic force, okay, and long range gravitational force, but it doesn't care about what happened in this region. Okay. And furthermore, we expect that in this region E mu nu will be small, okay, and as a result the expression for T mu nu simplifies, right, because you can now expand the gravitational energy momentum tensor in a power series in E. And these equations then can be solved iteratively and give the results that I quoted earlier. So here I have written down the formulae, the set of equations that we solve iteratively. Okay. So these are the expressions for the energy momentum tensor of the matter energy momentum tensor. Okay. This is T mu nu, which is the sum of the matter and gravitational energy momentum tensor. The only part that I have not written in this slide, but which you have to use, is the expression for TH in terms of E, okay, which is of course a very complicated expression, right, but it's something that is known. The most important part of this is how we put the boundary condition, okay? And this is where the analysis differs from the usual classical analysis, okay, and this is in fact the lesson we learn from soft theorem or quantum field theory. Okay. In normal classical analysis, the way you will set up a problem is that you will give the initial condition, okay, and then you try to calculate the particle trajectories in the final state as well as the radiation. Okay. That's a very complicated problem and we really don't know how to solve it, right? That depends on the details of the interaction. Okay. But the way we put the boundary condition here is that we assume that we know the incoming particles and the outgoing particles. Okay. So we put the boundary condition for the incoming particles in the past and the outgoing particles in the future. And then we can evolve these equations backwards and these equations forward. Okay. So the leading analysis, the leading contribution will come when we just substitute the dx d tau equal to p and dx d tau equal to p prime, substitute in this formula, you get T, and then you solve this equation. Okay? That gives the memory term, right? That's one in one go. Then we do one iteration. Okay, you get the 1 over u piece, and then in the next iteration you get the 1 over u square log u piece. Right? So this is the way we get the various parts of 1 over u of u, or equivalently the parts of log omega over omega, or omega log omega. Yes.
How is the scattering region defined? You said you wanted it to have a finite space-time volume, but now you're setting the boundary conditions off at infinity.
Yeah, so because you are solving the equation outside the scattering region. Indeed, so this is the scattering region.
Yeah.
But you are solving the equations outside the scattering region. Right, because you argued that the contribution from the scattering region can be ignored as far as the non-analytic terms are concerned. And when you are trying to solve the equations outside the scattering region, for the incoming states, we put the ingoing boundary condition.
So I should think of tau goes to infinity as the boundary of the scattering region? Or?
No, tau equal to 0 as the boundary of the scattering region.
Oh, 0.
And then tau goes to minus infinity for the incoming particles, and tau goes to infinity for the outgoing particles. Right? So we put the boundary condition as incoming particles from far past and outgoing particles in the far future.
But you've decided on those trajectories that the gravitational interaction between these masses is negligible.
No, it's important. That's what gives the corrections, right?
Okay.
But other interactions are negligible. If there is a nuclear interaction going on, that will be all inside the scattering region.
Okay.
It's only the long-range gravitational force and possibly electromagnetic force that are acting in the outside the scattering region.
But those gravitational interactions are no longer changing the trajectory.
No, they are.
Yeah.
Yeah, because we have to solve this, right?
Okay.
If you look at this equation that he described, we have to solve these equations.
Yeah, okay.
Right? So they are changing the trajectory. Otherwise, there will be no radiation. I mean, so this is important.
Okay.
Sorry, I didn't understand the sentence you said about solving the equation backwards.
Yeah, this equation, for example, you see we are putting the boundary condition at future infinity, right? Because we know the outgoing particle momentum. And that's at tau goes to plus infinity. And we are solving it backwards from there to find out what happened at early tau. Question?
And you could infer how things behave at late times instead of assuming it. And if you had fields, then this would not be so hard. It would be, let's say you start with minimal coupling, you solve the equations of motion, you derive the follows, and then
Yeah. If you knew the full interaction, in principle, you could solve inside the scattering region, right? And you could find out what the final state particles are. But then that will depend on the details of the interaction. Well, asymptotically, because you only need the long-range forces, right? So there it's only gravity and electromagnetism. Yeah, so then you don't need, so that's what you are using. That. No, that's what you are doing, right? So the difficulty would have been if you had to solve the equation inside the scattering region, right? Because there the interactions can be very strong. There can be nuclear forces, for example, that is going on, right? And we don't want to do that. Right? We are solving the asymptotic trajectories based on only the long-range gravitational and electromagnetic interaction, right? Because that's what these equations tell us. Right? We are using these equations, so these equations are the effect of long-range gravitational and electromagnetic interaction. Because you solve it iteratively, right? We calculate mu by solving this, then substitute it back here to calculate the particle trajectory, right? Then calculate the energy momentum tensor, then put it back again, right? That's the way you would do this iteration.
Far away, so that there is really a scattering region when you're solving for this.
Not really. That just depends. I mean, if the region is big, that basically means that the formula that I'm giving will be valid for later value of u. Right? So it's a question of how large u has to be for this formula to be valid. It will just increase that limit. Okay. Now possible generalizations. Okay, there is reason to believe that the coefficient of the u to the minus n minus 1 log u to the n, these terms may also have universal properties, okay, namely that they depend only on the momenta of the particles. Okay, and the question is, can we compute them? Soft theorem is not useful anymore because soft theorem is known only up to subleading order. But direct classical analysis may be possible, right? And in fact, this is still work in progress. I was hoping that we will get there before this conference, but we haven't gone there. Okay? So it's still in progress. Okay? And the ultimate goal will be to use these results in reverse, right? Because we can certainly measure the gravitational waveform from any scattering process. And if we are, if we measure it with sufficient accuracy, we can, in principle, extract the coefficients of the u to the minus n minus 1 log u to the n terms from the gravitational waveform. Okay. And then the question will be, is it possible to use this data to reconstruct the initial and the final states of the event that led to the production of the gravitational wave? Yes. Okay, I'll show you the result for electromagnetism, and maybe you can say how it looks. Now, even for electromagnetism, okay, for electromagnetism, the point is you have the full solution. Okay? And it is indeed true that the result can be expressed in terms of the initial and final momenta. Okay? Unfortunately, the result is a bit complicated to write down for general scattering. Right? We have the result, okay, but it's complicated so that I cannot write it on a slide. Okay? So what I've done here is that I have written it for 2 to 2 scattering. And for 2 to 2 scattering, in fact, there is a simplification because it takes the exponential form. This expansion, you can in principle resum and write it as an exponential.
And you think there's a chance you could write that generally? Because I thought the subleading soft theorem would have angular momentum type terms, which would be derivatives with respect to t disappearing, versus this looks like the soft factor.
See, those angular momenta become classical angular momentum, right? Yeah, and so this is derived by direct classical analysis, not using soft theorem. So you can try to reinterpret this in terms of soft theorem, but I don't know whether there's an underlying soft theorem for this. Okay, because this requires going beyond subleading, right? And we don't know whether there is a. No, this has exponential form. Yeah, this can be, you can easily see, right, that the structure is such that it can be written in exponential form. But for general scattering, we don't know how to write it in exponential form. That seems much more complicated for m to n scattering, right? Only for 2 to 2 scattering, it simplifies. Yes.
So you might have thought that as you keep going to further subleading orders in U, then other, like higher order terms, like if I have an R cube term or an R to the 4th term in my GR action, gravitational interactions are not just governed by GR, but by any like higher order corrective term, that they'll also show up.
Though those show up not in this leading series, right? But yeah, if you just drop one part of log u, then they'll start showing up, right? Angular momentum, for example, shows up at 1 over u square, right? Whereas 1 over u square log u is universal, depends only on the momenta.
So all of these formulas are basically just coming from like the Ricci scalar term
Oh, you are talking about the higher order corrections to GR Lagrangian?
Yeah, I'm asking like if I have
Riemann square. Okay, no, those we checked. It doesn't contribute to this order, right? U to the minus, the particular order that you are looking for, right? To this order, they don't contribute, the higher order terms. So this is, in that sense, it's really universal, right? The formula that I'm showing is robust. It doesn't get affected by
so if I was
those
looking
stuff.
at like you had 1 over u to the n plus 1, but I was looking at some subleading power in the log.
Yeah.
Then that will
That could get a lot of corrections indeed. In fact, that will also get corrections from the multiple moments of the external particles, right? Tidal love numbers. All those will enter once you go beyond this leading series.
Is there any chance you get exponential form if you try to write it as an operator acting on the amplitude of the level or something instead of as the answer?
At least we don't know how to do that, right? Exponential form.
For 2 going to 2, it can be written as exponential thing, and then this exponential of this angular momentum operator operating on this iconal, classical iconal part can be rewritten, but not the full S matrix we don't know. So that's why the quantum soft theorem can also be written. We don't know.
Also for m goes to n, we really don't know how to do that. Yeah.
We don't know how to
Yeah.
do that.
I have to ask the obligatory question. Is there going to be some double copy relation between this and the gravitational?
Well, that's how you're hoping that, I mean, the fact that this exists
It's
gives us confidence that you can get the gravitational one, right?
Yeah.
But what that formula is, we don't know.
You have the gravitational one already, or are you hoping to?
No, we don't have.
You don't have.
Yeah, we don't have. See, these people wrote down a conjectured formula for gravitational one.
Right.
That conjecture was given for general M to N, but I don't think that is valid because even for electromagnetism, right, the answer is more complicated than the formula that they proposed. But the 2-2-2 formula is very close to this, right? So I have a feeling that the 2-2-2 formula probably is correct, but general M to N requires modification.
You check this using soft limits of this formula. Is that what you do?
No, it just, the structure looks similar.
I see.
Right? The gravitational one, the 2-2-2 conjecture that they made, that has a very similar structure.
Can I ask? Because
Yes.
for 222, or for the binary waveform, there's a paper from like 15 years ago by the Mortagar, where they exponentiated these IR tails.
Okay.
This in the multipolar waveform, not the fully. And there the interpretation was just that once that the radiation leaves the binary, it just rescatters against the Newtonian potential of the binary itself. Does this have the same origin?
Yeah, so there are two effects, yeah. So, see, in electromagnetism, there is no rescattering, right? So this is for electromagnetism. This is coming basically from the Coulomb radiation. Right? So for gravitation, there are two effects. One is the rescattering, and the other one is the Coulomb, the fact that the final states are also accelerating under each other's gravitational influence. So they keep radiating. So it's a combination of the two that is responsible for the formula. Okay, so I think my time is up, so I'll put up the last slide, okay, which is some further related developments. Okay. First, there is a analysis from asymptotic symmetry. Okay, so at least for the up to the sub-subleading results that I showed, I think the soft theorem can be the asymptotic symmetry can be used to get those results. As I said, the results that I showed you so far are independent of the spins of the external particles, but the coefficients of the u to the minus 2 terms are spin dependent. These are semi-universal and they can also be derived from either soft theorem or direct classical analysis. So you have to look at this paper for that. And there are quantum versions of the soft theorem that involve corrections to the amplitude of this type. Okay, again, which I'll not discuss here. Now I had two more slides. Since this is a conference on celestial holography, I thought I should say something about flat space holography, okay, which has nothing to do with this talk. Okay, but just some comments on the flat space holography. Why I think that it's a different ball game compared to the ADS holography. Okay, so let me just say this quickly, but that's completely independent. So let's take a theory that you know exists. Okay? Let's take a theory that you know exists, which is type 2 on T6. Okay, that's a 4-dimensional theory. So let's suppose that we have a holographic version of that. Okay, that we know how to calculate the S matrix, all observables in that theory. If you have it, okay, then you could get all these different, all observables or all these different theories from there. Okay? Because starting from this 3 plus 1 dimensional theory, you can create arbitrary large configurations to arbitrary accuracy, okay, where you have these spacetimes. So you can send your experimentalists do the experiments here, and you can measure all the observables of all these theories, including ADS, okay, from this 3 plus 1 dimensional asymptotic space-time. This is very different from ADS. Okay. In ADS, if you have a theory with some moduli, okay, the moduli basically gets frozen to their asymptotic values. Right? You cannot create arbitrarily large space-time inside an ADS where the moduli take different values. So that's the reason why in ADS, for example, the dual theory, if you take say type 2b on ADS 5 times S5, okay, it has a dilaton, okay, but the dilaton expectation value, okay, is not a modulus. You cannot change the dilaton expectation value arbitrarily. It's fixed by this value at infinity, and that's the coupling constant of the Young-Mills theory. Okay, you cannot simply say that if you have a Young-Mills theory at one coupling, you can measure Young-Mills theory at any other coupling. Whereas you can do that in flat space-time. So this suggests that the holographic description of string theory in flat space-time is likely to be more challenging, but also more rewarding, because if you can get it, right, then you not only get the holographic theory of holographic description of one theory, but you get holographic description of all of these. Okay, thank you.